Good morning. So I want to spend a minute talking about the lab. I'll talk about the test, and we'll see if there are questions on the homework and so forth. So for those of you that are in the lab on that lab report, hopefully you downloaded the template. And mainly, there are three graphs that you have to do. Okay, so one of those graphs is the first one, plot, graph, whatever you want to call it. This axis is time in seconds. This is velocity in centimeters per second. So that should be linear. You should have a plot. You do a scatter plot and you get points that should be linear. Okay, do a best fit line. I mean, all of this should be in the procedure, but I know it's confusing to read sometimes. Best fit line and display equation. So y equals mx plus b. Okay. So if you're in Excel, and I'm sure Google Sheets has it as well, if you're using that, you can display the equation of the line. Then the procedure or the report template asks you a few questions about the line and what's T naught, okay, where's the intercept, things like that. Make sure that you label the axes. Now, I put a little label over here, but most of them, okay, time in seconds, and this is velocity, well, whatever it is, velocity in centimeters per second. Okay, something like that. Okay, that's plot one. Also, make sure that you put this in a box and you have a title. Velocity versus time. Whatever you want to name it. That's plot one. For plot two, you're plotting position versus time. This is position, and that's in centimeters, which the position in this lab procedure is S. That's not so great because seconds are, given as S, but it's just notation. You kind of have to get used to it. So you get something that looks like this. Okay, it should be polynomial of order 2. So you're going to do a best fit line for that. And in Excel, I'm sure Google Sheets has the same kind of thing. You fit this to a poly of order 2. Okay. Display the equation. You're going to get an equation that's of the form y equals ax squared plus bx plus c. Okay, it's going to be a second order polynomial. I think that's all you have to do with that one. And then for plot 3, you're going to redo plot 1. So here's time, here's velocity in centimeters per second. This is time in seconds. Okay, so you're going to redo plot 1. You'll have a nice best fit line there. Then I ask you to calculate the area underneath this line. Call this T1, call this T2. Shade the area, which you can do it by hand if you want to. You can do it with a pencil and draw it on there is fine. You can find a way, I know there's a way in Excel that you can make this area shaded, but I'm not requiring you to go to all that trouble. You can just do it by hand. Then you're looking at the area underneath this line between T1 and T2, and you compare it. What's the area underneath a velocity versus time plot? That's position, or that's displacement. So you look at S of T2 minus S of T1 from the previous plot, because you just plotted S, this is position, okay, not time. This is S versus T, okay, and then you compare that to the area underneath the curve here, okay? How do you calculate the area of a parallelogram? Well, you can look it up, but it's just, 1/2 H1 plus H2 times the base, I think. Okay. I can't think of anything else. I'm not looking at the procedure, so you need to be following what that procedure that is on my webpage. That's a generic sort of procedure. You need to follow the template, what the template asks you to do. And by the way, on this report, the template is not sort of a answer the questions kind of thing. It's a guide. You should write your report in complete sentences, explaining what you saw in the video and your calculations and so forth. So, don't just say like, did the object speed up as it fell? Maybe that was, I know that's not in there, but then you say, yes. No, I don't want that. It's not a question and answer kind of thing. It's a guide. It's a template. So, are there any questions on this? On the worksheet for the acceleration along a ramp, I'm not too worried about that. Just do the calculations and calculate those accelerations, and you're good on that. And I'll have something for you on these labs. I know time is so short. I'll have something for you on these labs this week shortly. So let's see. Yeah. Anyway. Are there any questions on that? Are you there? Okay.
All right. I had a question about the horn.
Yeah, sure.
Let me just.
Okay. All right, let me open mine up here.
It's problem 10.
Okay.
For chapter 5, sorry.
Okay, yeah. Problem 10, chapter 5.
Yeah.
Okay, I'm getting there. Okay, this is an elevator problem. So an elevator has two equal masses attached to the ceiling as shown. In my problem, they're 4.10 kilograms. Yours should be something similar to that. The elevator ascends with an acceleration of magnitude 1.00 meters per second squared. What are the tensions in the two strings? Okay, it's a good problem. All right, so let's look at the lower mass. I'll draw the whole thing. I'll call this, I think that they're both the same mass, aren't they? Okay. All right, so this whole thing is accelerating upwards. It's ascending, it's accelerating. And you want to know what's this tension in this string and what's the tension in this string. All right? Or rope or cable or whatever you want to call it. So let's look at the forces acting on the lower mass. On the lower mass, there is mg and T. And that's it. Okay? And we know that it has an acceleration in this direction. Well, I've got it in up. Okay? There's only one dimension here, that's the y direction, so I can use Newton's second law in the y direction and sum up the forces. Up is positive, so you get T minus mg equals ma. Okay? Yeah? All right. So the tension is equal to mg plus ma. Think if it were at rest, the tension would just be mg, but it's accelerating, so you get that extra force that you have to make the object accelerate. Okay, fine. That's the lower mass. Now let's look at this mass. For this one, I'm going to rename this T1. T1 is here, okay? Now for the upper mass, it's upper. If I draw the free body diagram, that's M. Then you have the support cable up here. I'll call that T2. Then there is the force mg, and from the third law, there is the force T1 in that direction. So mass 2, or this upper mass, has to accelerate not only this cable has to not only accelerate itself, but it has to accelerate that mass as well. So for the T2, which I'm calling the tension in the upper, this is T1, this is T2, you have T2 minus T1 that was just calculated here, minus mg is equal to ma. Okay? So T2 is equal to T1 plus mg plus ma. Okay? So that's how you would calculate the tension in that upper cable, T. I guess I got them backwards. They called that upper one T1, sorry. Because you know the mass and you know the acceleration. Now for part B, the maximum tension the strings can withstand is 91.8 newtons. What is the maximum acceleration of the elevator so that a string does not break? Well, I'm sorry for getting these switched, but T2 is going to have that maximum tension. So you can calculate T, given that tension T2, you can calculate the maximum acceleration. You have to go backwards, right? Yeah. Okay. T1 is just mg plus ma. So you can replace this T1 with mg plus ma, and you get T2, which I called it T2, 2 times mg plus ma. Then you can plug in that whatever it was, 91 and mine, 91.8 newtons, and calculate A. Does that answer your question?
I believe it does.
Okay. All right, are there any other questions on the homework problems, chapters 5 and 6? All right.
Sorry, can you repeat that?
What's that?
What did you say?
I said, are there any other questions on the homework?
Oh, okay.
Chapters 5 and 6.
Well, not at this moment.
Okay. Great, you got them all done. You're perfect. Got a perfect score. Good. Okay. So let's talk about our test tomorrow. I'll tell you what's going to be on the test. This is test 2. Number 1, a no friction, simple force problem. Like an object is on a flat surface and here's some force. You know, what's the acceleration? What's the normal force? What's all that stuff, okay? Frictionless. Straightforward, simple problem. Number 2. Again, no friction, but something with an inclined plane. So remember that on the inclined plane, that normal force is mg cosine theta, and the force along the plane is mg sine theta. So, okay. In all these problems, you need to follow those good problem-solving skills. Draw a free body diagram, label, name things. Write down the stuff you know. So, I really don't see how you can do these problems without a free body diagram. Students try it all the time. You guys have more time, because I'm just going to send it to you, then you got a couple hours to do it, or an hour and a half at least. But in-class tests, people are just furiously writing, and they're not drawing free body diagrams. I can't imagine how you would do it. And you draw a coordinate system, you apply Newton's second law, forces on the left, they equal ma. You look at each mass separately, whatever it is, okay? Number 3. Number 3 will be something with friction, like maybe like the one with the objects on the table with the string. So it'll be friction and 2 masses. Okay, maybe a flat surface and a hanging mass, something like that. Number 4, we'll do an inclined plane with friction. Okay. Two masses, more than likely. So an object on an inclined plane connected to a string, one of those magic strings with a magic pulley, and calculate the acceleration. Maybe it's going uphill, maybe it's going downhill, something like that. Number 5 will be a centripetal force problem. An object is rotating what's the centripetal force, or how much force do you need to keep the object in a circular rotation, this kind of thing. Bonus, okay, I'll give you a bonus of some kind. A bonus based on test 1, something from test 1. Probably won't be any more than 5%. Okay. Give you a bonus problem. And on my bonus problems, no partial credit. I'm looking for the answer, and the answer has to be exact. When I say exact, I don't mean significant figures, but it has to be the correct answer with units. Okay? No partial credit on the bonus. Are there any questions on that?
What time tomorrow do you want us to send you the lab at?
To send me the lab, 5 o'clock Central Time. Anytime tomorrow. As long as you get it in by tomorrow evening, that's fine.
All right. Thank you.
Sure. Any questions on anything else, stuff that we talked about yesterday or day before, about just overall, maybe conceptual questions about force and acceleration and friction and all of that stuff? Okay. So I'll lecture for a little while today on energy. This next section is about energy. Hear this word all the time. Energy conservation, saving energy, using too much energy. What is it? What is energy? Anybody out there take a shot at it? Give me some definition for energy. Can you hold it in your hands? Can you, I don't know. What is it?
Isn't it like the ability to do work?
Well, that's the technical definition, that's for sure, yeah. Yeah, it is. It's the ability to do work. We know energy by how we interact with it, okay? I like to think about different forms of energy. It can take many different forms. Certainly, I'll write down some of these. Solar energy, heat, thermal energy. Well, let's just say thermal energy. And all of these, we'll get into this idea of the ability to do work in a minute when we start talking about what we mean by work. What's the physics definition of work? Solar, thermal energy, chemical energy, electrical energy, nuclear energy. Keep going. There's all different, takes all different kinds of forms. energy is stored in chemicals and so forth, and chemical processes. There's electromagnetism, there's energy in electromagnetic fields, and so forth. Potential, I'll just say, the general sort of things we're talking about. Potential energy. Potential energy is, for the most part, what we're talking about now will be this energy of position, energy that's stored in a gravitational system or energy that's stored in a spring mass system, that kind of thing. So that's potential energy. There's also kinetic energy. This is the energy of motion. When an object is in motion relative to another object, then there is an amount of energy due to its motion. Okay, you know this from everyday experience. So that's what we call kinetic energy, this energy of motion. What are the units of energy? Anybody happen to know? Any old unit of energy.
Joule.
A joule. Yeah, go ahead. A joule. Yeah, named after Joule. Okay, Joule did some very early careful work about the mechanical equivalent of heat. So he looked at this relationship between thermal energy and mechanical energy, like stirring a substance and the temperature of the substance increasing because it was stirred. So, yeah, Joule, James Prescott Joule. Let's see. The fundamental units are a kilogram meter squared per second squared. And we'll talk about that in a minute. Okay. A joule is a kilogram meter squared per second squared. A joule is a tiny little bit of energy. A calorie, just to give you a feel for the magnitude of this energy, a calorie is 4.184 joules. Last time I looked, I think that's still the same. So a calorie is equal to 4.184 joules. That's a thermal energy calorie, okay? When you look at food and you look at the energy they claim is available in a candy bar or something like that, and they say, well, it's 100 calories or it's 500 calories, or you should get 1,200 calories per day according to the US government or something like that, okay? That's actually a kilocalorie. So when you're looking at food calories, those are kilocalories, okay? So one food calorie, I'll call it, this is terrible, but no, I don't know, is equal to 4,184 joules, okay? It's a kilocalorie, right? So anyway, a joule is a little small amount of energy. Okay. Let's talk about this relationship to work. Because someone just mentioned that energy is this ability to do work. So an object has some energy if it has some ability to do work. But what is work? Okay. Well, when we say work in physics, we mean something fairly specific, and it's at a very basic level. It is a force times a distance. Okay? It's a force through a distance. It's actually a force, well, that's fine. It's a force through a distance right now. Okay? So, force has units of kilogram meter per second squared. Distance has units of meters. And that's where you get that kilogram meter squared per second squared. That's a joule. All right? You take a newton of force through a meter of distance, that's 1 joule. All right, so let's look at our object, some box or some such thing sitting on the floor, and here is a force, okay? I'm just looking at magnitudes right now. We'll look at how we deal with the vectors here in a minute. So let's say there's some force and it pushes the box a distance or a displacement for us, delta R. Okay? So you move the box some distance delta R. Then the work done by this particular force, we're going to talk about net work done on an object, just like we talked about the net force on an object equaling ma. We can talk about the net work done on an object, and we'll get some relationship between work and kinetic energy. That's going to come later. So the work that would be done, and just like I said, the work would be equal to F delta R. That's it. Work is a scalar. It is not a vector. A lot of times you really want it to be a vector, like, man, this force is pushing this object in this direction and increasing its kinetic energy and so forth. Kinetic energy, which we'll talk about eventually, is not a vector. Work is a scalar. It's an amount. Right? It doesn't have a direction. Energy is a scalar. It's not a vector. It doesn't have a direction. Okay, energy north or something. This is just at a very basic, force times a distance or times a displacement. And let me see. I'll get rid of this. For simple constant forces, okay? So when we're looking at constant forces, so this means that the direction and the magnitude of the force is not changing throughout the motion, all right? Then the work is equal to F dot delta R. It's the force dotted, and I'll tell you what that means in a minute. Some of you may already know. It's the force dotted with the displacement. This is a vector multiplication. This is called the dot product or scalar product. Most people call it the dot product, as opposed to the cross product, which we'll eventually get to. And multiplying these two vectors together gives you a scalar. So this is a dot product, sometimes called the scalar product. Okay? So when you dot two vectors together, and since we're talking about forces and displacements, let me look at, let's say this is delta R, and the force is here, okay, in this direction, and there's an angle between F and delta R of theta. This dot product, what it does for you is it gives you a projection of F onto delta R. Okay, or it gives you a projection of delta R onto F. It'll be the same thing. This length, that projection of F onto delta R, that length, as you know, is F cosine theta. That is the adjacent side of that right triangle that I just formed. This is called a projection onto delta R. So the only thing that really counts for the work that makes a difference is the projection of the force, or the amount of the force that's in the direction of the displacement. And I'll show you, I'll explain that more to you in a minute. So this F dot delta R, now we're talking about constant forces. This is equal to F delta R cosine theta. So it's that magnitude of F, magnitude of delta R, and the cosine of the angle between them. And it's really this amount of force in the direction of the displacement. Okay? Forces that are at a right angle to the displacement do no work. They're not speeding up the object or slowing the object down in that direct, well, they're not, okay? If the object's displacement is horizontal, then any component of the force that's perpendicular to that displacement does no work. All right? Like the normal force oftentimes does no work. The gravitational force, as I'm walking across this floor, that gravitational force is down, it's following me around, but it's doing no work. If I decide to jump up on this table, okay, then there is some force, gravitational force, and the displacement are in the same direction or opposite direction. And there's some work done, okay, by the gravitational force. All right, you could have a situation where the displacement delta R is in this direction and the force is this way. Okay? This angle is something greater than 90. And if that force is in this direction and it's going that way, that is a negative amount of work. You can do a negative amount of work. That is not a direction. Okay? You can have a negative bank account. You can have a positive bank account. Mine's usually teeter-tottering there somewhere between positive and negative. Try to keep it a little above, you know, that zero level. But anyway, the work can definitely be negative. All right? Forces that are in the opposite direction of displacement do negative amounts of work. Okay? All right. So this is the idea. When you're looking at the force, you're looking at a particular force, and you want to know the work done by that force on the object, and we'll talk about semantics eventually, like the work done by some outside agent on an object, or the work done by the object on an outside agent, okay, or an external agent. Anyway, this is what you need to know for constant forces. F delta R cosine theta is the work. It's that amount of F in the direction of delta R. Okay? Obviously, if the angle, let's look at angles. If the angle is 0, it's just like I drew in the first case. It's F delta R. It's just the magnitude of the force times the distance. If the force is 90 degrees, cosine of 90 is 0, okay? So you get no work done by that force that's perpendicular. If the force is 180 degrees to the displacement, cosine of 180 is negative 1. That's a negative amount of, well, it'd be negative F delta R, okay? And we will see how all this works. I want to spend a minute talking about this scalar product or this dot product and how you calculate the dot product. So we've already seen that. I'm just going to use two vectors, just vectors in general, A and B, okay? So A dot B is equal to AB cosine theta. Just for any two all vectors you meet on the street, okay? If you want to know their dot product, it's AB cosine theta. This dot product is commutative. A dot B equals B dot A. Okay? Doesn't matter how you dot them. All right? The negatives work just like you would think. The negative of A dot B is negative A dot B or A dot negative B. Okay? Distributive, if you have A, let me put it like this, A dot B plus C. This will distribute just like you would expect. That's A dot B plus A dot C. Okay? Nothing weird there. When we get to the cross product or the vector product, some of this changes. Cross products, anti-commute, and so forth. Okay, so I want to show you how to do this dot product in component form. It's super, super easy. I'll do it in 2 dimensions. A is equal to AX I hat plus AY J hat. Like always, this works perfectly fine for 3 dimensions. No worries, or 4 dimensions or 5 dimensions. B is BX I hat plus BY J hat. Okay. So if I write out A dot B, that's equal to AX I hat plus AY J hat dotted with BX I hat plus BY J hat. Okay, by this. So we do what we always do. We FOIL this out. These are 2 binomials, and all the algebra operations are perfectly fine for dot products. They distribute the way they should and so forth. So let me do that. So I'm going to distribute this one first. I have AX, BX, I hat, dot I hat. Well, I hat dot I hat, if you're dotting the same vector with itself, the angle between those two is 0. I dot I hat is going to be 1. Because these are unit vectors. I hat dot I hat is equal to 1. These have unit length. They're the same vector, so the angle between them is 0. So it's 1 times 1 cosine 0, which is 1. So the first term here, AX I hat dot BX I hat, is simply equal to AX BX. Let's look at the second term. I'm going to distribute this here. AX BY I hat dot J hat. Well, I hat is in this direction. J hat is in this direction. That's the X direction, that's the Y direction. The angle between I hat and J hat is 90, cosine 90 is 0, okay? I hat dot J hat is equal to 0, okay? If you project J hat onto I hat, there is no projection. There's no component of J hat in the I hat direction, nor is there any component of I hat in the J hat direction. That's what these dot products are. They're projections. Okay? So this is equal to 0. I don't get a contribution from AX BY. Let's take this term. AY J hat dot BX I hat. Same game. J hat dot I hat, that's just these commuted. That's equal to 0. Now for the last term. AY BY J hat dot J hat. Well, that's just like I hat dot I hat. J hat dot J hat is equal to 1. Same vector, they both have unit length. The angle between them is 0. Cosine 0 is 1. So this is AY BY. That's it. That's A dot B in component form. You multiply the components, keeping the x's together, the y's together, the z's together, and you add them all up. Very, very easy to take the dot product in component form. Much more difficult to take the dot oftentimes. Much more difficult to take the dot product by the other way where we had A, B cosine theta, because sometimes it's difficult to find out what that angle between two vectors is. Very, very simple in component form. AX BX plus AY BY plus AZ BZ. Keep going as many dimensions as you like. Okay. Any questions on this? All right, so I will look at some examples. All right. Whoa. Okay. Are you guys, someone still there? I've been talking for a while.
Yeah, we're here.
All right. Thank you. Okay. Here's an object on a frictionless surface. Here's a force. This force is 15 newtons, and this angle is 30 degrees. All right. So let's say that this object moves from here, so starting here and ends up over here, and it has a displacement delta R that is equal to 3.0 meters. How much work was done on the object by the 15 Newton force? Well, work is equal to F dot delta R, but we know from what we just did, it's F delta R cosine theta. Okay, I mean, this is pretty darn simple. F is equal to 15 newtons. Delta R is equal to 3 meters. And then there's a cosine of 30 degrees. So this is equal to 45. By the way, a Newton meter is a joule, okay? I didn't state that explicitly, but a force times a distance, I wrote down a kilogram meter per second squared, which is a Newton. So a force times a distance is a Newton meter. So this is 45 times the square root of 3 over 2. I think that's the cosine of 30. So this is equal to 22.5 square roots of 3 joules. I don't know what that works out to be, but okay. What about that component of the force that was in the y direction? Well, that force, that component did no work. Some external agent has some stored energy, and they're doing work on this object, moving it along through some distance delta r. Okay. Any questions on that? Pretty simple. You may see some cases where you have two vectors, a force vector and a, let me show you that real quick, because that may be in the homework. I won't. Let's say there is a force that is Fx I hat plus Fy j hat. And remember, these are constant forces, okay? And the displacement delta r is equal to Rx I hat. This is just the same thing I just did, except, looking at the notation that you would see. How much work is done by that force through that displacement, delta r? You just take the dot product, F dot delta r, and that's equal to Fx Rx plus Fy Ry. Okay? That's the idea. A hockey puck slides across the floor, has a displacement, there's some force on it from air resistance, whatever it may be, and you're given that. So the work, I guess I should write work. Okay. So doing a net amount of work, like I said, you can look at the work done by individual forces. This force that's in the opposite direction of displacement, or a force that's in the direction of displacement, or a normal force, or a gravitational force, and so forth. Okay, you can look at all the work done by those forces individually. And when you sum up that work, okay, the net work done on an object, okay? So the net work that is done on an object by summing up all the work is equal to the change in kinetic energy. So this, when I write Ke, that is kinetic energy. I'm going to write down the definition or the form of kinetic energy for point particles. So a point particle meaning a rigid, you can think of it as like a steel ball with a particular mass, okay? Kinetic energy, and I'll derive this later, is equal to 1/2 mv squared, okay? 1/2 mv squared. So it goes like v squared. The kinetic energy, this energy of motion, depends on the mass and the velocity of the object. It is a scalar. There's no, even though velocity is here, v squared means v dot v. When you square a vector, when you're squaring a vector and you're getting a scalar, that means v dot v. Okay? You're looking at the magnitude of the vector squared. Okay? And that's what that gives you. Okay, so it's 1/2 of the mass times the velocity squared. And this relationship, this so-called work-energy relationship, okay, if I write it out, the change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. It's the change in the velocity from some initial condition to some final condition. If the final velocity is greater than the initial velocity, something did a positive amount of work on the system. There was a net positive amount of work. That would be like a force increasing the velocity of an object. Okay? A force pushing an object, increasing its velocity, and V final is greater than V initial, then something did a positive amount of work on the system or the object. If V final is less than V initial, that would be a negative amount of work. That is, something did a negative amount of work on the system, something slowed it down, like friction. Kinetic friction always acts in the opposite, in the direction opposite to the velocity, right? Kinetic friction always does a negative amount of work on a system. Okay? So it slows things down. It decreases the kinetic energy of a system. What else do I want to say about that? We're going to do lots of examples based on this. Oh, I know what I was going to tell you. So this physics student is walking down the street and this big truck is rumbling by and it's carrying a load of bricks. And this brick flies off the truck and hits the physics student in the head, knocks him out. And he finally awakens, comes to, there's a crowd around, and he starts smiling. And somebody looks at him and says, "Why are you smiling? You just got knocked out by a flying brick." He said, "Well, I'm just really glad kinetic energy is 1/2 mv squared." Okay, I know I can't hear your just bursts of laughter with that joke, but okay. The emphasis on 1/2. All right. So tomorrow we'll have the test. I am going to go ahead and, I'm not going to do a live lecture, but I'm going to post some examples of work energy, forces through distances, and how we're going to handle all that, because most everything I did today was theoretical. All right, are there any other questions? If not, I will say see you later.